Hi everyone. Feels like it's been so long since we've seen each other in a video form. So I want to talk about two quick things. First thing is the fundamental theorem of algebra. Okay. So the fundamental theorem of algebra states that any polynomial of degree n has n roots. So really simply, the highest exponent that a polynomial has that same amount of roots or zeros or x-intercepts or solutions. Okay. So we talk about quadratics a lot. Quadratics obviously have the highest root of 2, or I'm sorry, the highest degree of 2, which is how many roots it has? 2. Okay? So, remember that there's zeros, solutions, or x-intercepts. Moving on. Okay, now we're going to dig into this really deep. But I want to go kind of segmented for the first week of class regarding this concept, because there's a lot of pieces, a lot of loose ends that we have to kind of tie together here. One thing that I want you to keep in the back of your mind is the beginning of this table. Now we're going to continue this table to about 7, right? 6 or 7. But I want to make sure that you are understanding of the breakdown of these things. So to start, we're going to focus on 1 and 2 for purposes of tonight. Tomorrow we'll get more into the third root because there's some methodology there with factoring that you're not really familiar with. So again, if it's got degree 1, that means it's linear, right? We're talking about a linear function, which means it has 1 root. Meaning the possible combination, there is only 1. It's 1 real root, okay? Like a real number root, all right? If it has degree 2, we're talking about a quadratic polynomial, and it's got 2 roots. Not at most 2, it has 2, okay? So it's got to be the exact number of the degree. Very easy to remember. Now, the combinations, as you're aware, when we solve quadratics are, they could be 2 real roots, right? So if I have a regular, normal, kind of run-of-the-mill quadratic, I get x equals 4 and x equals negative 2. Those are 2 real roots, okay? Now, I want to make a little bit of a kind of specific change here. Real and complex, so complex numbers have real parts to them, okay? So what that means is we're talking about a plus bi or a minus bi. The a part is the real part. So you're going to see me reference more often real/complex as the roots. Now, in this instance, I would replace this word complex with imaginary. So think about it like this. We've got the real side of the spectrum, which are integers, numbers that we talk about all the time. We move towards imaginary, which is the far other end of the spectrum, which is straight up, I, or 2i, or 4i, whatever. In the middle is kind of where they meet, right? So we're talking about like 7 plus 3i. Well, the 7, the positive 7 there, would be the real part of the imaginary number, but it's not. It's complex, so there's kind of a pattern there. So it's either a quadratic polynomial, it either has 2 real roots or it has 2 imaginary roots. It doesn't have one or the other, right? Now, there's a reason for why complex roots or imaginary roots can't be 1, 3, or 5. Okay, so we'll talk about that in a second. Then we go to 3, and then we go to 4. Now, as you can see with the table here, we talk about 2 complex roots or 2 imaginary roots, 2 imaginary roots, 2 imaginary roots, or 4 imaginary roots when we get to a 4 here. Now, here is the reason for that, and then I'll cut this short. When we talk about quadratics, imaginary roots have to come in pairs, meaning they're complex conjugates of each other. So if I have 6 plus I, the conjugate is also a root, 6 minus I. And we did conjugates when we divided with imaginary numbers, right? Because we had to make the complex conjugate on the denominator in order to get rid of the imaginary part of the denominator. Because kind of like with radicals, you can't have a radical in the denominator. Same with imaginary. Same here. So knowing that a complex conjugate, a conjugate of a root that's imaginary is just the opposite sign, is going to be incredibly helpful for you moving forward. Okay? So basically this video, remember that n degree means n roots, and we're going to start with 1 and 2. And that was kind of your homework that you had to work on tonight. 2 real, 2 complex, fundamental theorem of algebra. Don't forget this. It's not going anywhere. All right? See ya.